My name is Archita and Emily Kunti, and I am a junior at Hopkinton High School.
I'm Srija Bola, and I'm a sophomore at Hopkinton High School.
And for our science fair project during the year of 2019 to 2020, we created a sensor that diagnoses neonatal anemia non-invasively in newborn babies. And the whole idea behind this project really just came in the summer of 2019 when I found out that I was going to have a baby sister. So I wanted to create a sensor that can diagnose a condition that is tested invasively in newborn babies to minimize the amount of stress that newborns go through. So the problem with the neonatal anemia diagnostic test, it's called CBC, it's invasive and it has potential negative side effects on the newborn, such as decreasing cardiovascular reserve and low blood concentrations. So we created a sensor that can diagnose neonatal anemia non-invasively, and it does that by first determining the light absorption of a protein called fetal hemoglobin, and then it calculates the concentration of fetal hemoglobin using a principle called Beer's law. And then it determines whether the patient has anemia based off of the calculated hemoglobin concentration.
So we decided that for our procedure, the baby's finger would be placed inside the sensor, and then their hemoglobin concentration would be calculated. The first problem that we faced during this is that hemoglobin is not the only protein that absorbs light. There's the skin, there's the hormones in the blood, and there's obviously other proteins. So we decided to use a method called photoplethysmography, which is also used in pulse oximetry, in order to only analyze the hemoglobin. So on the right, you can see a graph of how we separated the blood and then the skin absorbance in order to exclusively analyze the hemoglobin. So there's actually two different forms of hemoglobin that we needed to analyze for this, the oxygenated form and the deoxygenated form. So when oxygen is added to hemoglobin, it changes its structure, so it absorbs light in different ways. So in order to analyze these separately, we use their absorbance spectra and compare them against each other in order to separate each of them.
And the sensor also makes sure that the light passing through the finger travels in a straight line. It makes sure that the photons have a low energy, and thereby having them travel in a straight line, and ultimately having the sensor display an accurate result. And then once the sensor takes into account all of these factors that we just described, it then calculates the concentration of fetal hemoglobin using this standard curve, y equals 0.025x, where x represents the concentration of fetal hemoglobin and y the absorbance.
So the standard benchmark for newborns is 13.5 grams per deciliters. So this is what the concentration determined by our sensor would be compared against. So if it's greater than this concentration, the newborn does not have anemia. And if it's less than this concentration, the newborn's diagnosed with anemia. So this is our sensor's design. On the left, it's the white case that surrounds the sensor, and it's used to reflect outside light back out and not interfere with the readings. And on the right, it's a diagram of our sensor that includes its microcontroller, its Bluetooth module, and the two light sources, the infrared and the red light, in order to analyze the oxygenated and oxygenated and deoxygenated versions. And then the photodetector, which receives the transmitted light.
So the whole process starts off when the sensor is plugged into power. And once it's plugged into power, it starts calculating the light absorbance of the deoxygenated hemoglobin derivative. And then it goes on to determine the light absorption of the oxygenated hemoglobin derivative. And then it calculates the total hemoglobin absorbance and then on to the total hemoglobin concentration using the standard curve. And then it determines anemia by comparing with the standard benchmark. And then it sends the diagnosis to an Android app in a phone, which displays the result.
So the diagnosis is sent through a Bluetooth channel, which is established using our Bluetooth module. So either a 1, a positive result for anemia is sent, or a 0, a negative result saying that the baby does not have anemia. So, and this diagnosis is displayed on the phone as either the baby having anemia or not.
This is the sensor code. It is programmed in C language. And this is the app code. It's programmed in Java using Android app development.
Since we obviously couldn't test our sensor on newborn babies, we had 5 adult subjects. So we knew these subjects conditioned beforehand. We knew whether they were anemic or not anemic. And then we did 10 trials on each subject. So we tested our sensor on them 10 times. And with all 50 trials, we found that our sensor's diagnosis matched the subject's actual condition. So we had a 100% accuracy rate.
Thank you all for listening to our project. We just want to say thanks to Sanofi Genzyme for sponsoring this award, and thank you to MSEF for giving us the opportunity to pursue our passion and pursue our research project. So thank you for listening to our project.
Yeah. Okay. Hi, this is Lieutenant Governor Karen Polito. I just want to congratulate both of you for this amazing effort and outcome, truly impactful on the health of babies, inspired by your own personal experience being a big sister and wanting the best for your younger brother or sister, I'm not sure. But I just want to ask you, first of all, you developed your ideas around you have a problem to solve. Can you just elaborate on the problem solving process? You make it look so easy in your presentation, which was beautifully done, but clearly there was a lot of analysis and research and development, maybe some frustration along the way that both of you had to struggle through. Just describe that a little bit for us. I can't hear you. Here you go.
Okay, so we faced many problems in the research biology end and the technology computer science end. For the biology end, we had to take into account all the factors, all of the things that were happening in the finger. We had to make sure that the light traveled in a straight line. We had to take into account the oxygenated and deoxygenated hemoglobin. And, we had to take into account those factors. As for the technology and computer science side, we had to make sure that our algorithm worked and it displayed the correct result. So we had to continuously revise our code and make sure that the results were accurate.
Srisha, I'm sure you had a lot to do with this process.
One of the biggest things that we encountered was that our code wasn't like lining up properly, so it wasn't timing itself. And we had to write a lot of revisions in order to have 2 threads of code, which is called multi-threadings, to run like simultaneously.
How much time did you spend as a team working through this process?
We had some designated hours at school that we had to attend, but a lot of it was done at home. So we would meet at least twice a week, I think, at least like 4 times in the beginning. And we had to establish a plan very quickly. And a lot of it picked up intensity along the end when we had to finish our presentation and get our results.
So toward the end, I know others have questions too. Toward the end, though, you probably had to pivot to a remote setting where you didn't have as much in-person time with each other to solve. So pivoting to something very challenging was something you had to include in your plan.
Mm-hmm.
Yes, especially like the presentation part of it. Yes.
And a lot of it, we were kind of just going back and forth between our houses and trading the sensor and our poster between each other in order to finish it in time.
So I just thank you to Bill Seibold and the team at Sanofi Genzyme. Did your office serve as a mentor role in any of this? It seems like these two are incredible students and thinkers but was there some guidance along the way that helped them get from one point to the next?
Not with this. We have mentors. We've been having mentors for years and years, and we have served in a mentorship capacity and also in judging at some of these. But just these two are very special people that have just managed to put together just a world-class project, let alone a high school project. So congratulations to them.
Do we have any more time for questions?
Okay.
It strikes me as a sophomore and a junior, you had exposure obviously to science curriculum, but then to take those concepts and apply them to the problem to solve is very advanced thinking. I guess I'm just trying to figure out, how did you learn this? How much research did you do? How did you do that?
Beer's law. We learned it in our chemistry class. So we definitely had to do a lot of research outside of the school, especially in the physics aspect, like the scattering constant. So we spent a lot of time doing research on that. But we started off launching from what we learned in school.
If you could change anything about your education in high school, what advice would you have for me as your lieutenant governor to change or to add to education across the Commonwealth around science, math, engineering, technology?
I would just think to make things more independent and project-based. I think that way students get more excited about what they're doing, and it gets more about learning and discovering new things than about getting a grade.
Great. Maybe I could ask a question to the two of you. So what's next with this project? I mean, this is a technology that you've created, an idea that you've created that has a lot of application to it, and you're sitting in perhaps the greatest place in the world to take an idea and actually turn it into something that people will use perhaps all over the world. So have you thought about what's next?
I'm pursuing a continuation project next year that is related to diagnosing not just anemia, but also something called thalassemia, alpha and beta, which is just a deformation in hemoglobin, and also sickle cell anemia. So not just one test, but two more, so that newborns don't have to go through so much stress when they're born.
Fantastic.
Awesome. And Archita and Srija, I have a question about the coding part of your project. How did you learn to code? How did you have to teach yourself? Did you learn that in school? Would love to know more about that.
In our school, there's a course called AP Computer Science Principles that Srija is taking right now. I took last year. And then there's also a Java class at our school that we took.
And a lot of it is just searching up videos to teach yourself and like learning formulas and algorithms.
Both of you are in high school. Was there something in middle school that was impactful in terms of your appreciation of your own abilities around science and math? Like, many students in middle school begin to shy away from the harder STEM subjects rather than go and lean in. You obviously leaned in. So is there something we can learn from your experience in middle school that helped you?
think like so I think like students should get involved more into science when they're in middle school. Get involved in like science fair and just be more curious about learning science.
For me, I didn't do science fair when I was in middle school, but I did get interested in science through my like science class. And I found that my science teachers, especially in 7th and 8th grade, were very impactful there because they really encouraged like projects and learning on your own. So I kind of like applied that into science fair.
Amazing. Thank you both for your incredible presentation. And I know that lots of folks may have questions afterwards to reach out to both of you, but thank you both for your incredible work. And I think I can speak on behalf of all of us that we are very excited to see where you will go next and are very grateful to have you in our state working alongside of us. So a huge thank you to both Archita and Srija. We are so grateful, and both also to Sanofi Genzyme for all of your wonderful work, Bill, and all of this to support this great effort. And with that, we are going to turn over to a video from MathWorks to kick off our second presentation.
Hello, my name is PJ Boardman, and on behalf of MathWorks, I'm very pleased to address you this morning as part of STEM Week's opening ceremony here in our great Commonwealth of Massachusetts. MathWorks is committed to accelerating the pace of engineering and science by ensuring that students and professionals around the world have the best possible tools for design and innovation to increase human knowledge and to profoundly improve our standard of living. To do this, we strongly believe we need diversity, equity, and inclusion in STEM education and in our workforce. Today, more than ever before, the call for equality and social reform underscores the importance of diversity in STEM professions and the imperative to inspire students of all genders and races to pursue STEM studies and careers. This imperative is reflected in this year's Massachusetts STEM Week theme of See Yourself in STEM. It's not just about breaking through barriers, it's about shattering stereotypes. And it's also about the essential need for role models and mentors, particularly for students from underrepresented groups. MathWorks has a long history of developing and supporting STEM education programs worldwide. Through these programs, our staff engages with students through hands-on projects, mentoring, and sharing career experiences, with the goal of inspiring them to explore and to achieve more. We are so proud to partner with organizations like MSEF who share these goals with us. Our partnership goes back more than a decade, and we are so happy to have contributed to the growth and success of the program over the years. Each year, we sponsor scholarships for teachers to participate in MSEF's Curious Minds initiatives. It's a professional development program aimed at integrating science and engineering practices into curricula. Over the years, our staff has volunteered as judges at the MSEF middle and high school fairs and participated in the expo with interactive demos. Through these fairs, students had the opportunity to apply the same methods and critical thinking used by professionals to innovate, to challenge conventions, and to advance our understanding of the world. A great example of one such student is this year's MSEF MathWorks awardee, Suvin Sundararajan, a senior from Westfield High School. When Suvin was just a junior, he designed a process for synthesizing filament in fused deposition modeling. His hard work and dedication to explore STEM beyond the classroom is impressive. Not only is Suvin an accomplished student, but he also won a first-place award at the International Science and Engineering Fair last year. On behalf of MathWorks, I'd like to send our sincere congratulations to Suvin and to all the teachers and students who are doing such extraordinary work in these times. You are truly our heroes, and you inspire us each day as you build our next generation of scientists and engineers. I'd now like to invite Suvin to share a bit more about his MSEF project, and I want to wish all of you an amazing experience during STEM Week. Suvin, cheers to you. The floor is now yours.
All right, thank you very much. It is an honor to receive this first place MathWorks Award at the State Science Fair and represent Westfield. My name is Suvin Sunarajan, and let's begin. So my project this year was functionalized polylactide filament for additive manufacturing. And this is a continuation within 3 years. And I actually wanted to address a lot of things in this project. Some of the main things I wanted to decide on was about the societal needs for safer plastics. We all know that the main problems are that most plastics aren't reusable, and a lot of them really contribute badly to pollution. We also have a lesser known issue about flame retardants, as most of them are halogenated, which contain fluorines, bromines, and chlorides, which release toxic chemicals. And so these two problems really made me want to make this better. Like, I wanted to make this feel a lot better and incorporate this in 3D printing. And some good examples of this are like the PFAS, which contaminated drinking water, a known halogenated flame retardant, as well as increasing global warming, as we can see in the West Coast. So what I did is I created a filament that can be used for 3D printing, that improves flame retardants, and develop a modular approach that can be used to incorporate other project properties in the future, because that's what we want to do. I want to set the standards for how we do this in the future, because PLA is a hard material to work with. PLA is the most common filament for additive manufacturing. And the bottom shows a manufacturing process of how I went from the raw materials all the way to the FDM 3D printing on the right. To synthesize the flame retardant, we actually have to do this because it is not a compound available commercially. To do this, we synthesize using two monomers, BHTB and BPA, and combine them through a process and made a polymer. Now, a polymer is a series of long chains of repeating units, and this is how we did it through a reaction. And as you can see on the right, this is the reaction in progress, and this non-halogenated compound is perfectly safe as it burns, which is a major selling point, and is non-toxic. So once we create this compound, we then have to synthesize the filament itself. Now, we can't do it with the raw materials. We have to do a lot of different processes within it. So first we take the raw materials and then put it in a batch mixer. This machine melts and mixes to create a homogeneous mixture, which is what we want. Now, these two compounds, PLA and the deoxybenzoate copolymer, are both miscible, which means they blend very well, which is something I discovered in this. After we have this compound, we get this nice gooey liquid, which we can then put in an extruder. An extruder takes this and then outputs like a filament, a thin line that can be used with consistent diameter. Now, this part actually was the part that had a lot of difficulty in the project because it was kind of like, it really didn't work well. So I actually had to design a little bit of the robotics kit to actually pull the filament. Professor Brazil's touching story about the AI and robotics really inspired me as well. And this is something that played a big role in saving the project because we could be able to have consistent filament. The reason why we need a consistent filament is actually for the printer, because without it, it wouldn't work. Before we can get to the printer though, we have to actually CAD model the designs we want to use for the printer. I use software, which is a free one called Tinkercad, but you can also use other ones such as Autodesk or Inventor Pro. And you can create these 3D models that actually are really nice and then transfer them to the 3D printer. These models were both made by me. Once we have the models, we then can convert it onto the printer. And on the left is an example of the roll I made. This is more than 2 meters of filament that had to be extruded out. And this was put onto the 3D printer. After you 3D print this is going on the same settings as normal PLA, which makes it a lot easier for the end user. We then have a couple things I printed here. Now, a fire hydrant is here for irony purposes because this is going to be a flame test. And also we have a thin filament rod, or a thin tensile rod that can be used for testing. I know time is short, so I just wanted to show a couple of the main characterization I did, but trust me, there's a lot of them here. But this is called FTIR, or Fourier Transform Infrared. This is a way we can measure the spectrum of these compounds. Now, we wanted to measure the compounds because, simply put, we need to make sure that our blend that I made has both of them incorporated. The top is PLA and the bottom is deoxybenzoate copolymer, and the middle is my blend. Based on these circles, you can see that different groups, such as the ketone group, are actually incorporated in different parts of the polymer, and each little peak represents a potential group in the compound in the molecule. And this is useful to ensure that, yes, this is indeed the polymer we want. We also had to do thermal analysis because, of course, flame retardants, fire, we should probably do that. So one of the main things I tested was the heat release capacity. Heat release capacity, it determines how well it burns and the rate at which heat is released. This is very important because low values predict low flammability, which is what you want in consumer applications. Over here, you can see this is PLA, the original sample we had, as well as the flame retardant PLA that I made. Previous attempts have tried to do this, but it hasn't fallen short because they use small molecules. Using this long polymer chain, we were able to decrease the heat release by 20%, which is a lot more than what has been previously done. And as you can see here on the right, this is a comparison to other polyesters, which is the type of polymer this is. There's a lot of different types of polymers. This is one of them, as well as other filaments if you're into 3D printing, such as ABS and other flame retardants, which are a lot more expensive. My flame retardant here performs, like I said, 20% better, and also in a category where is it acceptable for flame retardants in commercial applications. There's also other data I did, such as TGA, which measured the amount of weight percent at the end, and others such as DSC, which characterized how exothermic or endothermic, meaning it releases certain heat at different times. Those aren't shown here, but if you'd like more information, please let me know. Now, what can we do with this? Now that we have a polymer that works, what can we do? I showed that this successfully implemented flame retardants into this filament, and it can be used for a lot of different fields, such as aerospace, residential construction, and more. Actually, one of the most prominent examples of polymers in this is the Boeing Dreamliner, which is a well-known plane that uses polymer parts for a lot of different aspects, such as panels, bezels, and cast materials. I mean, polymers are in everyday life, and I'm sure you all know this, but polymers play a huge role, and without them, we won't be able to have a running society at this point. The flame retardant materials are also useful in housing, and especially useful now during the wildfires in the West. And this is something that can be useful in more applications. Now, I want to mention that science isn't done alone. As I'm sure the other group knows, and we all know that there's a lot of people that provide help. And even though a lot of the ideas were made, there are still many people I have to thank in this. First off, I have to thank my high school, Westfield High, for supporting my research all the way through, as well as the UMass Polymer Science and Engineering Department for letting me use their labs and their mentors. Professor Todd Emmerich, Elizabeth Studs, and Chris Cueto were very helpful mentors in this progress that helped me guide along the way. And of course, I have to thank my family here. I hope you all enjoyed that, and I'm really excited for the future of polymers, and this is one step out of many. This is, like I said, been 3 years of this project, and it's going to be continue on from here.
That's fantastic, Subin. How did it feel to have your name right on that the form that you created for the 3D printer?
It was pretty cool. Like, it was a lot of I honestly, that day I was kind of bored. So I was like, why don't I just put my name here, see how it works? And it actually was more complicated because you think just when you write your name on something, like on a piece of paper, it just prints off there. But when you're 3D printing, it adds a whole nother complexity to it. Like,
well, you should be proud of that, right? You own that. I mean, it was your thinking and the others that assisted you. Why do you think your project came to the top of the pile? Like, you won the award with some pretty significant competition in this science and engineering fair.
I think a couple things can be attributed to that. First off, I really am enthusiastic about this project. I think that I want that to carry through, and I'm pretty sure hopefully it can through this presentation, because this is something I deeply care about. I really wanted to have work on polymers. I remember freshman year, I didn't even know a whole lot about science in general. I honestly, when I went to the science fair, I didn't know that MSEF existed. And it was something working on thin filaments and thinking, hey, I could do a little more with this instead of because I really looked up a project for my freshman year and then realized, wait a minute, there's more to this. Let me explore it. And I think that enthusiasm is really what drove my project and allowed me to get a lot of data analysis and also do other stuff and contact mentors and network.
That was the answer I was looking for, right? I mean, the competition and the award is just a small piece of it. It really is your passion for math and the science that went behind your developing and discovering a new process that can really be impactful.
Exactly. Yeah.
Yep. Let's expand on that.
Okay, so it's really something, but it's also meeting new people, meeting like-minded people and learning how they do stuff, where you can adapt a little bit here and there. You can learn more about the science process as a whole. Because actually, when I first started this project, a year ago, this is a continuation, I didn't know chemistry at all. So it was all learning from the ground up, because I didn't take AP Chem and I didn't take computer science. So this is an interdisciplinary project that requires a lot of attention. And I wanted to address a bunch of different topics in here. So I just started learning things here and there.
But how much of this did you discover through your classroom and your teachers' efforts with you versus what you did outside of the classroom? I mean, coming up with the analysis around a long polymer chain versus small molecule and arriving at the conclusion you did to then design your project around is pretty huge.
Mm-hmm. Yep. I see what you're saying. So at the high school, I got access to like lab resources, like a little bit and here and there. And then I really took it forward by working with UMass and then learning more about how other scientists function, like how they work. And it was a lot of it actually reading a lot of papers on my own time. Like I read probably, I think I have a list. I think I've read around 200 or 300 research papers just about this topic, just to like learn more, because I need, like, if I'm going to do a project on this and say like, okay, I'm making this better filament, better polymer, I do want to be credible and I do want to have that knowledge to back it up. So it requires a lot of research, and a lot of that research was done on my own time. My mentors really helped in guiding me where to go, but also providing the training required for some of these machines. Like some of these complex machines, I think the NMRs that I use, like which are like nuclear magnetic resonance, they're like multi-million-dollar machines. And people are training me on how to use them because these are pretty essential in a lot of chemistry labs. And this is something, learning that experience through mentorship and learning those, how to use those experience, allowed me to understand how they function. Like, and I could start getting ideas off it saying, oh, maybe I could use this analysis to prove this point. And then once I prove that point, maybe I can use something else behind that to also further push what I'm saying.
It's just interesting because if you did not have this exposure before high school, but then your project included, you know, principles around engineering and math and AI and chemistry, and so many different subjects are involved in your project. How did you know how to solve this?
I didn't. I'm going to be honest. I was sitting here in December of last year, sitting, what am I doing? I'm sitting here 8 weeks. I've been trying to figure out this filament problem where it wasn't even a chemistry problem. It was just pulling out the filament. And I thought that's really simple. And a lot of these issues, like a lot of these thinking of interdisciplinary like ideas like chemistry or physics, come down to problems in the project. I mean, if it all worked on the first try, I wouldn't need to use robotics. I wouldn't need to make complicated systems for that. But because of these problems, it allowed me to explore further in these fields, learn more about it, because I didn't really program. I honestly didn't like programming at all 4 or 5 years back. And now that I realize how useful it is, I can start combining different systems here. This is something I'm working on. Like as we speak, like yesterday I was tinkering with this to make something better for the system and go on that idea of making a better puller for this filament system. And
is that one of the reasons why you think problems don't get solved? Because people get frustrated and give up versus persevere through, which is something that you did.
I think, yeah, that's a really good point, because a lot of problems are genuinely hard. Like they're really difficult to solve. And I did get frustrated at times too. Like it sometimes is when something simple really doesn't work, but it's a lot of different steps. And something I learned from my mentor this year was that chemistry, like if you're doing newer chemistry, 9 out of the 10 things fail. And that's something, going with that expectation of, okay, this is I'm gonna fail, this may or may not work, is probably the attitude I'd go towards and suggest others, because I know there are high schools, I know my own class is watching this, and people are wondering, how do I do a science fair like this? And the first thing to do is accept the failures, accept that that's gonna happen. Look, this project, I was ready to say this was gonna not work. I had that option in this. I sort of got lucky after a lot of perseverance of trial and error that this ended up working. But in that, you come with new ideas, and it's a really cool process, honestly.
I guess not being afraid to fail is part of that too.
Yep.
Alexis.
That's the first step towards success too. Like, and even like, the thing is, I'm really glad to experience these kinds of failures like firsthand, because this happens like every other year, but like this was the first year where I was stuck for 8-9 weeks, just not knowing what to do. And that made me rethink a lot of stuff too, like the process. Like when it's easy to say, okay, this seems like impressive, this seems like a lot of work. But when you sit through and realize like the amount of problems and a lot of things, you start to have a deeper understanding of the topic as a whole.
That's incredible, Subin. Thank you so much for all of those questions. I'm actually going to turn it over to my colleague at MIT, Rohan.
Yeah, Subin, thank you so much for that wonderful presentation. I think that comment you made at the end about failure being one of the main things of doing scientific research and engineering research is very apt. Every science engineer watching this right now is nodding their head vigorously, because that is one of the biggest points of science and engineering, is to never giving up when you fail 99 out of 100 times. I had one other question. So it sounds like you've participated, so as one of the MSEF winners, you've participated in the International Science and Engineering Fairs now for a few years. Could you maybe talk about what your experience has been when you were able to go last year and what this year was like? And what's the coolest part of being able to attend an international science and engineering fair?
Yeah, sure. I'm sorry. I know there's some like loud noise outside for lawn mowing, so please ignore that. But ISEF allowed me to connect with other mentors, other people like around Massachusetts. Like there were really great people on like the Boston side and like the middle central Massachusetts, and it was allowed everybody to get connected in Arizona. It was also a new place. I never went to the west side of the US, and I was like, oh my God, it's 100 degrees. So I was experiencing a different life there, but also just, it was great being there with collected with so many people. Like I think there were 2,000 people at this fair participating and competing. And you also meet a lot of judges there. Like it is actually very similar to MSEF, and hats off to MSEF for making it very similar to ISEF too, because I felt really prepared for this fair. It was 12 judges, which took hours and hours, but I was already prepared for like, because we went through like 5 or 6 at MSEF. And it was really cool because I actually got a judge from Massachusetts. And it made it even better because you can have these connections with different judges, but the MSEF really prepared me for making those connections outside. And one of the things being virtual, like I know MSEF was virtual, and it actually was a really good transition because it's like sort of like a different competition where you have to adapt to presenting your work, to how can you market the ideas and show, yes, this is what we did in a short amount of time.
Great, thank you. So many things you're talking about really represent the characteristics of a good science and engineer. And same thing with Archita and Srija, that flexibility and adaptability is one of the best qualities you've definitely shown through all of your projects. If we don't have any other questions, I just want to say thank you again, Suvin, for that wonderful presentation. Thank you to MathWorks for sponsoring this prize. And to end off this second hour, I would like to hand it back to Helen Rosenfeld, the Executive Director for MSEF, who is going to share with us a few other opportunities MSEF is going to be hosting later on during this Massachusetts STEM Week. Helen?
Great. Thank you, Rohan. And thank you to Suvin, to Archita and Srija for really digging into this. And I think they looked a little shell-shocked when I asked them to shift their year-long research into 5 minutes speaking points. And you've done an exceptional job of making it in, putting it in layman's terms for all of us. And your enthusiasm is infectious, and we're just really pleased to have you in our circle. So thank you. I also just want to extend a few more thanks before we wrap up. I want to use this opportunity to thank MIT, President Reif and Paul Paravano. Thank you so much for serving as hosts of our fair for the past 71 years. MIT has been our valued partner, and they provide both this inspiration and aspirational model for our students who convene from across the Commonwealth in the pursuit of science and engineering. And thanks to our supporters. We were honored to have Sanofi Genzyme and MathWorks with us today. I want to also let Cabot Corporation share in the spotlight because they've sponsored our middle school fair for over 20 years. And there are countless of other institutions who add tremendous value to the institutional and student experience, whether as judges, coaches, or underwriters. And it takes an ecosystem to do this work. Thank you, Governor Baker, Lieutenant Governor Polito. Thank you to the STEM co-chairs, Dr. Leiden and Congressman Kennedy, and to Secretary Pizer for prioritizing STEM education. And thank you to the teachers, the administrators, the parents, and most importantly, the students who put in the hard work and whose curiosity, persistence, and innovation are going to lead us into a very exciting future. So you can find us at scifair.com and get informed. And if you're interested in getting more involved, please email us at info@scifair.com. You can join us later this week. On Thursday, we're having 2 of our regional sessions. One is a Metro North session. The other is a Central Mass session, both on Thursday afternoon. You can find details about that on the STEM Week website. And I just really want to thank everyone for having us join today. It's been a pleasure.
That's great. Thank you.
All right, thank you so much, Helen. And I just want to give a couple other thank yous as we wrap up this morning. So a huge thank you to MSEF, to MIT, to all of our speakers this morning. My name is Alexis Legan, and I serve as the director of the Massachusetts STEM Advisory Council. Despite every challenge put in front of them, our regional STEM network managers across the Commonwealth have pushed through and worked diligently to organize a robust, engaging, and inclusive STEM week, and I could not be more grateful for all of them. Also, a big thank you to MK Montgomery on my team working alongside me here at EOE, working to make sure that STEM Week programming is accessible in a virtual world. So thank you. Now more than ever, equity and inclusion in STEM learning and in STEM sectors is critical. And my hope is that this week will serve as a catalyst for these conversations, opportunities, and a space for action that will continue beyond STEM Week. Fueled by the passion of our incredible young students, Archita, Srija, and Suvin included, and through STEM learning, my hope is that these conversations and opportunities contribute to leaving the Commonwealth and the world a better place for all than how we found it. So for a full listing of over 300 events, activities, lessons throughout the week, please visit www.massstemweek.org and follow along on social media at Mass STEM Week on Twitter and Instagram. So thank you all so much. A huge thank you to my fellow MC Rohan here with me, and happy STEM Week, everyone.